Quantum radar, detecting objects before reflection, the physics of seeing without echoes. Imagine standing in complete darkness and knowing something is there not because you heard it, not because light bounced back to your eyes, but because space itself subtly changed when you looked. That idea sounds abstract, almost philosophical, yet this is exactly the direction modern sensing science is heading. Quantum radar represents a fundamental shift away from classical detection based on reflected energy toward a new model based on quantum correlations, information theory, and probabilistic inference. It does not rely on louder signals or stronger transmitters. It relies on deeper physics. To understand quantum radar, we must first understand the limits of classical perception. Traditional radar systems operate on a simple physical principle: emit electromagnetic waves, wait for them to reflect, and measure how long they take to return. The distance to an object is calculated using the equation d equals c at a tilde, delta t slash 2, where c is the speed of light, approximately 300,000 kilometers per second, and I circumflex t is the round-trip travel time of the signal. If the pulse returns after 10 microseconds, the object is roughly 1.5 kilometers away. Velocity is derived from Doppler frequency shifts. Shape and size are inferred from signal scattering patterns. This approach has powered aviation, weather monitoring, astronomy, navigation, and telecommunications for nearly a century. But classical radar has unavoidable physical constraints. As distance increases, reflected energy falls off with a fourth power of range. This is called the radar range equation. Double the distance, and your returned signal becomes 16 times weaker. Eventually, reflections become indistinguishable from thermal noise, random electromagnetic radiation produced by the environment itself. At room temperature, every object emits microwave radiation continuously. That background noise overwhelms faint echoes. At absorption, scattering, atmospheric distortion, and electronic interference, and classical radar rapidly loses sensitivity. In other words, classical sensing depends on signal strength. Quantum radar does not. Quantum radar belongs to a broader family of technologies known as quantum sensing. Instead of detecting objects by measuring reflected power, quantum systems detect changes in quantum correlations. The difference may sound subtle, but it represents a complete paradigm shift. At the heart of quantum radar lies entanglement. Entanglement occurs when two particles are created together in a shared quantum state. Their properties such as phase, polarization, or timing become linked in a way that cannot be explained classically. Measure one particle, and you instantly gain statistical information about the other, even if they are separated by large distances. This does not transmit information faster than light. It simply means the two particles carry shared quantum structure. Quantum radar exploits the shared structure. The system begins by generating pairs of entangled photons using nonlinear crystals or superconducting circuits. A high-energy pump photon enters a special material and splits into two lower-energy photons through a process called spontaneous parametric down-conversion. These two photons are now quantum partners. One photon, called the signal, is transmitted into the environment. The other, called the idler, is stored locally in a quantum memory. The signal photon travels outward, interacting with everything in its path: air molecules, dust, surfaces, background radiation. Almost all of its delicate quantum state is destroyed by noise. In classical physics, that would mean the signal is lost. But quantum radar doesn't rely on preserving entanglement. It relies on preserving correlation statistics. Even when entanglement is broken, subtle statistical fingerprints remain between the noisy return signal and the retained idler photon. Specialized quantum receivers perform joint measurements on these two streams. Instead of looking for strong echoes, they look for matching quantum patterns hidden inside noise. This technique is called quantum illumination. The key insight is this: thermal noise is random, but entangled photons carry structure correlations. Even in environments where signal power drops below noise, correlation signatures can still be detected. Mathematically, quantum illumination offers up to a 6 decibel advantage in signal discrimination under high noise conditions. That may sound small, but 6 dB represents a fourfold improvement in detection probability. In extremely weak signal regimes, that difference is decisive. This means quantum radar can detect objects in environments where classical radar sees nothing at all. Let's translate that into physics. In classical radar, detection probability depends on signal-to-noise ratio SNR. If SNR falls below a threshold, detection fails. In quantum radar, detection depends on mutual information, the statistical correlation between transmitted and received quantum states. The system evaluates whether the returning photons share measurable structure with the stored idler photons. If correlation exceeds background expectations, something is present. No strong reflection is required. Detection becomes probabilistic rather than energetic. This is why people sometimes say quantum radar detects before reflection. It doesn't violate causality. Signals still travel at light speed. What changes is the detection mechanism. Instead of waiting for a clean echo, the system continuously evaluates correlation fields. Presence is inferred from information patterns rather than signal amplitude. This is sensing as information theory. Now consider timing. Traditional radar waits for echoes. That introduces latency equal to twice the distance divided by the speed of light. Quantum systems also obey this limit, but because detection is statistical and continuous, probability fields evolve in real time. The system doesn't wait for a perfect return pulse. It integrates correlation evidence as soon as photons interact with the environment. This creates the impression of near-instant detection. Modern laboratory quantum radar experiments operate at microwave frequencies between 5 and 10 gigahertz or optical frequencies around hundreds of terahertz. Photon pair generation rates can exceed 10 million pairs per second. Detection sensitivity reaches regimes where fewer than one photon per measurement window carries useful information. To put that in perspective, classical radar systems require millions or billions of photons to detect weak objects. Quantum systems can extract information from single photon correlations. Thermal background radiation becomes irrelevant because it is uncorrelated. This is the power of quantum statistics. Now add artificial intelligence. Quantum receivers produce enormous volumes of probabilistic data. Machine learning models are trained to recognize correlation signatures buried deep in noise. Neural networks learn the difference between random thermal fluctuations and genuine quantum returns. This hybrid quantum AI architecture dramatically improves detection confidence. Again, nothing becomes louder. Everything becomes smarter. Quantum radar also offers inherent resistance to interference. Classical radar can be jammed by injecting fake signals. Quantum systems cannot be spoofed the same way because attackers cannot replicate your entangled idler photons. Without access to the original quantum pairs, injected noise lacks the correct correlation structure. Security emerges naturally from physics. Zooming out further, quantum radar is only one piece of a much larger revolution. Quantum gravimeters use atom interferometry to measure tiny changes in gravity. Quantum magnetometers detect magnetic fields weaker than 1/trillionth of Earth's field. Optical lattice clocks achieve accuracy better than 1 second over the age of the universe. Quantum LiDAR promises millimeter-scale distance measurements over kilometers. All of these technologies rely on superposition, coherence, and entanglement. They measure reality using quantum states themselves. Future quantum sensor networks may map underground structures, monitor ocean currents, predict earthquakes, observe atmospheric chemistry, and detect disease biomarkers long before symptoms appear. This is not about conflict. This is about perception. At a deeper level, quantum sensing forces us to rethink measurement. Classical sensing treats the universe as passive. You send signals out and wait for them to bounce back. Quantum sensing treats measurement as interaction. Observation changes the system. Information is exchanged through entangled states. Detection becomes a dialogue between observer and reality. Information theory merges with quantum mechanics. Instead of asking, "Did my signal return?" quantum systems ask, "Did the universe respond differently because I asked?" That is a profound conceptual shift. Now imagine what happens when these systems scale. Quantum satellites distributing entangled photons globally. AI-driven quantum receivers operating at the edge. Environmental sensing with atomic precision. Planetary scale perception networks. We are moving toward a world where physical reality is continuously sampled at the quantum level. Earth becomes a sensor. Atmosphere becomes data. Space becomes a measurement medium. The boundaries between physics, computation, and perception begin to dissolve. But perhaps the most important transformation is philosophical. Quantum radar shows us that reality is not something we simply observe. It is something we participate in. Every measurement alters the universe, however slightly. Every observation leaves a trace. Quantum sensing makes this explicit. We are not separate from the systems we measure. We are embedded within them, and that realization changes everything. Curiosity ending high retention loop. If quantum systems can detect objects through noise, if entangled particles carry information across space, and if sensing no longer depends on echoes, then the next question becomes unavoidable. What else is the universe already communicating that we simply haven't learned how to hear yet? CTA Series Continuation. Subscribe for the next episode. how quantum sensors will map Earth with atomic precision, because the future of science isn't louder, it's quieter, smaller, and unimaginably deeper.